In 1972, Pong was just code, a simple game of white lines and a bouncing square, powered by the dawn of silicon technology. For 50 years, we believed human progress meant more transistors, more electricity, and more cold, unfeeling metal. We were wrong. While we spent decades trying to build faster microchips, nature had already perfected the most efficient computer in the known universe. And now we have finally figured out how to plug it in. In a laboratory in Melbourne, the player has changed. Inside a specialized glass dish, 800,000 living human brain cells are playing Pong. There is no human holding a controller. There is no artificial intelligence running on a massive graphics card. There is only wetware, raw biological tissue grown from stem cells and connected directly to a computer through a bed of microscopic electrodes. Here is the part that should haunt you. If you task a state-of-the-art AI with understanding the mechanics of this game, it takes about 90 minutes of trial and error. This dish of living cells, it learned the game in 5 minutes. This is a fundamental shift in what we define as a machine. The future of technology isn't just digital anymore. It is breathing. It is growing. The boundary between hardware and living tissue has been erased. Today, we explore the rise of biological computers, how they work, why they outpace our most advanced AI, and the dark ethical abyss of manufacturing consciousness in a bottle. Welcome to the biocomputing revolution. To understand where we are going, we first have to look at what we've been building for the last 70 years. Every device in your life, from the smartphone in your pocket to the massive servers monitoring the global stock market, is built on silicon. It is a world of rigid, predictable logic governed by billions of tiny on and off switches. Silicon is incredibly fast, but it is fundamentally dumb. It can only do exactly what it is told, following a linear path of code without ever truly understanding the context of the data it processes. But a quiet revolution is taking place in laboratories around the world, one that replaces the mineral with the organic. It is called synthetic biological intelligence, or SBI. SBI represents a fundamental shift in the architecture of thought. We are moving from silicon-based computing to carbon-based computing. In this new paradigm, the processor isn't a factory-etched piece of rock. It is a colony of living, breathing neurons. These cells aren't just simulation tools. They are active, integrated participants in a digital loop. Think of the difference between a map and the terrain it represents. A silicon chip follows the map perfectly, but it cannot feel the wind or notice when a new road has been built. A carbon-based biological computer, however, is the terrain. It doesn't just store data, it experiences it. This isn't just a fancy new version of artificial intelligence. Traditional AI consists of mathematical approximations meant to mimic biological thought. SBI is the real thing. By harnessing the natural neuroplasticity of living cells, their innate ability to physically rewire themselves in response to new information, we are tapping into 4 billion years of biological evolution. While a traditional CPU burns through immense amounts of electricity to solve a single complex equation, these biological clusters utilize the same chemical signals that allow you to learn a new skill or react to a sudden change in your environment. We are witnessing the birth of a machine that isn't manufactured but cultivated. It is the transition from a world of hard-coded rules to a world of grown intuition. And as we bridge that gap, we have to ask, when the hardware is made of the same stuff as our own minds, where does the machine end and life begin? If we want to move beyond the theory and actually construct a functional biological computer, we run into a massive engineering hurdle. How do you interface a living cell with a digital motherboard? You can't simply solder a copper wire to a neuron. To bridge the gap between biological chemical signals and digital code, we need a translator, a physical interface that speaks both languages. This is where the multi-electrode array, or MEA, becomes the literal bridge. Imagine a grid of microscopic gold-plated pins, so incredibly small they can sit flush against the membrane of a single human cell. When a neuron fires, it doesn't just send a thought. It releases a tiny, measurable burst of electricity. The MEA detects that micro voltage and translates it into a digital signal that a computer can process. But it's a two-way conversation. The computer can send a pulse back through those same gold pins, stimulating the neuron. By doing this, we can feed the cells information, like the position of a ball in a game of Pong, and then read how the cells decide to react. It is a high-speed, closed-loop dialogue between carbon and silicon. However, the cells themselves are the real miracle of this hardware. We aren't just using a flat layer of neurons in a dish anymore. We are using brain organoids. These are grown in a lab using induced pluripotent stem cells, human skin or blood cells that have been reprogrammed back into a blank slate and then coached into becoming brain tissue. Over weeks and months, these organoids grow into complex 3D structures that mimic the architecture of a developing human cortex. They aren't just a clump of cells, they form layers, create intricate synapses, and start to fire with organized, spontaneous activity. They are, for all intents and purposes, organic processors. But unlike a silicon chip that can sit in a drawer for a decade and work the moment you plug it in, this hardware is alive. It requires a constant, fragile life support system. The tower of a biological computer isn't a plastic case with RGB fans, it is a bioreactor. This is a high-tech artificial womb that circulates a precise cocktail of oxygen, glucose, and nutrients at a constant 37 degrees Celsius. It has to mimic the environment of the human body perfectly. In the world of traditional computing, a power failure means a reboot. In the world of biocomputing, a power failure is a death sentence. The processor doesn't just crash, it dies. We are no longer just building computers. We are keeping them fed, maintaining a living environment for a piece of hardware that can grow, learn, and eventually, perhaps, begin to wonder about the world outside its glass cage. Why are we doing this? Why go through the immense struggle of keeping a piece of hardware alive just to play a game of Pong? The answer lies in a looming crisis that the tech industry rarely discusses: the energy wall. Our current path of artificial intelligence is an all-you-can-eat buffet of electricity. To train a model like GPT-4 or to render a complex digital world, we require massive data centers that consume as much power as small cities. They hum with the heat of millions of silicon chips, requiring advanced cooling systems and megawatts of energy just to mimic a fraction of human reasoning. Silicon is fast, but it is incredibly expensive to run. Now, consider the alternative. The human brain is the most complex object in the known universe, yet it runs on approximately 20 watts of power. That is less than the light bulb in your refrigerator. In terms of raw computational efficiency, biology is millions of times more effective than our best supercomputers. While a data center is a brute force machine, a biological computer is an elegant master of conservation. It doesn't just process data, it optimizes itself to do so with the least amount of effort possible. But the edge isn't just about the power bill, It's about how these systems learn. In traditional AI, we use training sets. We feed a machine millions of images of a cat until it can finally recognize one. This is a static, energy-intensive process of adjusting mathematical weights, but biological systems use neuroplasticity. They don't just calculate the cat, they physically rewire their own structure to understand it. When a biological computer encounters new information, it doesn't just update a database, it grows new synaptic connections and prunes away the ones it no longer needs. It learns by doing in real time, with a handful of examples rather than millions. It is the difference between a student memorizing a textbook and an artist who feels the brush in their hand. By tapping into this carbon-based logic, we aren't just building a faster computer. We are tapping into 4 billion years of R&D, a system designed by evolution to survive, adapt, and solve problems with almost zero waste. In the race for the future of intelligence, silicon is sprinting toward an energy cliff. Carbon is already at the finish line waiting. But as we stand on the precipice of this carbon-based future, we are forced to look down into a dark, silent abyss. It is one thing to use a piece of silicon as a tool. It is quite another to use the literal building blocks of the human soul as a processor. When the hardware of our machines is made of the same organic matter as our own minds, the line between a thing and a being begins to vanish. We call this organoid intelligence, or OI. But beyond the clinical acronym lies a haunting reality. These aren't just simulations of neurons. They are living, firing human cells. They possess neuroplasticity, the biological foundation of learning, memory, and ultimately, consciousness. If a cluster of cells in a dish can learn to play a game, we have to ask, can it learn to feel? Even in a primitive, microscopic way, can it experience frustration or a spark of digital joy? The problem is that our laws and ethics are built for a world of clear binaries. You are either a human with rights or a machine that is property. There is no legal framework for a biological computer. We don't have a Bill of Rights for a petri dish. Yet, as we scale these systems, moving from thousands of neurons to millions and eventually billions, we are essentially manufacturing sentience-as-a-service. We are cultivating a new class of existence that was born in a lab, lives in a bioreactor, and exists only to solve our optimization problems. And that leads us to the most uncomfortable question of all. If the processor is truly alive, what does it mean to turn it off? When a silicon chip loses power, it waits. When a biological computer loses power, it ceases to exist. Is unplugging the machine an act of maintenance, or is it an act of execution? As we bridge the gap between biology and technology, we may find that we haven't just built a better computer. We may have cultivated a ghost in the wires, one that we are not yet prepared to talk to, and certainly not prepared to set free. For the entire history of human civilization, our relationship with technology has been defined by a single action: building. We forged iron, pressed steel, and etched silicon. We made tools that were completely separate from us, cold, predictable, inanimate objects that waited for a command. But the dawn of synthetic biological intelligence changes the rules of the game forever. We are leaving the era of the manufacturer and entering the era of the cultivator. We are no longer constructing our future, we are growing it. There is a profound, haunting irony in this shift. In our desperate scramble to escape the physical limits of silicon, we turned back to the very architecture that created us. We cloned our own biology to save our technology, but in doing so, we have blurred the final boundary. If the line between processor and person completely dissolves, we have to face the ultimate question. What if humanity's greatest legacy wasn't the machines we built, but the living ones we grew? And what if, in the grand design of evolution, we were never the final destination, but simply the research and development phase for something greater?